All right, so welcome to Chapter 9, Lecture A. This is about take 8 million, and by 8 million I mean take 3. So, generally, we have told you that a ionic compound, an ionic compound, is something that's a metal and a non-metal. And we've said that's called ionic. We've said that when you have, for a covalent, that's going to be 2 or more nonmetals. Well, the truth of the matter is, these are lies. And that's pretty much what a lot of chemistry is. We lie to give you an idea of how something works, a general trend, and then we fill in the gaps that we may have otherwise skipped over. So, the truth is, there's really only one kind of bond. It's called a bond. So there's bonds that have more ionic character, and there's bonds that have more covalent character. And the truth lies somewhere between these two things. So there's ones that are really, really ionic, and ones that are really, really covalent. And most things fall somewhere between this. So one way to think about that, let's just have an idea of what that means. If you have something that's totally covalent, you're looking at something that's like chlorine bonded with chlorine. Here's how I know. Chlorine wants an electron just as much as chlorine does. And because chlorine wants an electron as much as chlorine does, they pull this electron equally, and this bond is really evenly placed between these two things. So chlorine over here's got, let's take a step back and remember what chlorine is. So chlorine's in the 7th column, right? Being in the 7th column, it wants, these are representative of electrons. It has 7 valence electrons. So how many does it need to have? 8. It needs 1 more electron. So this guy needs 1. Then we have this chlorine over here. It also has 7 valence electrons because it's chlorine, and it needs 1 too. The ultimate goal of all atoms is to get 8 electrons. So this one needs 1, this one needs 1, and the best way to do that is this one's like, hey, can I borrow yours? And this one's like, yeah, only if you let me borrow yours. And they're like, okay, well, how about we just share? And that's a covalent bond. They're sharing this 1 electron. So now this one feels it's got its own electron, and then it feels like it's taking this one sometimes. And the same thing with this chlorine, it's got this one, and then it feels like it's taking this one sometimes. And again, the ultimate goal is to have 8, so they're relatively happy. Now, they're equally sharing this because they're both the same thing. So this one's pulling this way, this one's pulling this way. It's like a tug-of-war game between 2 equally sized people and size and strength people. Okay, then we move on to something that's ionic. The common example we usually give is like sodium chloride. Now, we don't draw a bond in sodium chloride because we know it's ionic, but let's say we did. Let's talk about what this bond would look like. Well, sodium is in the 1st column, so it has 1 electron. Chlorine, again, has 7. Now, there are 2 options sodium really has to get 8. It can gain 7 electrons somehow, so that would be pretty crazy. Or it can give this 1 electron off. Giving this electron off, now that we know and understand electron configuration, when something has an electron and it gives it off, now all of a sudden it's just like a noble gas before it, which would be over here. And so it can give this electron off to be like a noble gas. Well, if it gives it off, it's Na plus because it's lost an electron. And this chlorine's over here, like, I'll take that electron because again, it needs 1 to have 8, so it takes it, and now it has 8, and is super happy. Now, why these 2 things are really not all that different is here it just happened to be that they were equally sharing that electron. Here, chlorine's taking that electron, and it's like, I'll take all of it, and sodium, you can't have any. And most compounds lie somewhere in between these 2 things. So let's look at how we would determine what happens. So we already know that chlorine really, really likes electrons, right? Because it only needs 1 to have 8. And in fact, that's generally true in the entire periodic table is that up and to the right, and we discussed this in the last lecture, up and to the right, fluorine really likes electrons. Well, down here to the left, it doesn't. And that actually follows the same trend as size. So as we go up and to the right, fluorine's really small, right? And fluorine's really small because it loves electrons, so it's keeping them real tight. If you love something, you hold it close. So this guy's really small, and this guy down here is like, I don't care about electrons, you can do whatever, and it's really big. We call the love of electrons electronegativity when it's binding. So over here, chlorine is equally electronegative. Here, chloride is more electronegative than sodium. And because it's more electronegative means it loves electrons. So it's more electronegative, meaning it's loving electrons more than sodium, and that's why it gets one when it's in a bond. So going back to this periodic table, it actually assigns specific numbers for different electronegativity. Fluorine, again, being the highest, it's got a 4 right here. And you go down to like francium over here is 0.7. It's like, I don't care about electrons. Noble gases are excluded because they have 8, so they don't have electronegativity. They already have 8 electrons. They have 0 desire to take on extra electrons. Okay, so in understanding this, we can determine where something lies on this scale. In fact, we put a little difference right here at a difference of electronegativity of 1.7. Anything greater than 1.7 will be ionic, and anything less than 1.7 will be covalent. What I mean by more or less than 1.7 is a difference in electronegativity. Let's do a few examples. Let's start with like a carbon fluorine bond. So carbon has an electronegativity of 2.5, and fluorine has an electronegativity of 4.0. That's a difference of 1.5. So we go on this scale and we say, hey, anything less than 1.5, it falls somewhere here, is covalent. So this would be considered covalent. Now there's one more thing one more part of the scale. Let's put it here. This is purely covalent. Purely covalent is when there's no difference in electronegativity. An example of that would be this chlorine. They're both the same thing, but we'll do that here in a second just to make sure I drive that point home better. Okay, so carbon-fluorine bond is mostly covalent. It's not just strictly covalent, it's mostly covalent. Anything less than 1.7 is going to be mostly covalent. Unless it's 0, then it's purely covalent. Let's do another example. Let's say let's look at sodium chloride. Let's see where it lands on this scale. Sodium has an electronegativity of 0.9. Chlorine has an electronegativity, I think it's 3.0. Yep. And the difference here is 2.1. So on this scale that we've got, it's 2.1 is greater than, so it's telling you somewhere around here, it's mostly ionic. So you'll have questions on your homework that are really similar. You essentially list if something's mostly covalent or mostly ionic, and you do that by looking at the difference in electronegativity between those things. Let's move on to chlorine. You could do this with any diatomic, fluorine, etc., or any even polyatomic elements. Chlorine is 3.0, and chlorine is also 3.0. This has a difference of 0, and these are what you call purely covalent, meaning this is an actual covalent bond. This is the only real pure covalent bond that there is. Otherwise, things just have mostly ionic character, mostly covalent character, but there's really no difference. It's a bond. And so we need to understand that. Now, you can look at this doodah right here. This is from your Silverberg book, and you get an idea of what's going on. So as you get something like chlorine, diatomics, or fluorine, or bromine, anything like that, that's bonded with itself, it's going to be covalent. And then it gets more ionic as you add things that are farther away from on the periodic table, farther away metallically. So let's zoom back out. So if you have something from here paired with something down here, that's going to be more ionic. But as you move something from here paired with something from here, or the semi-metals, this is where you get kind of right in between the middle of somewhat ionic, somewhat covalent character. And so again, there's really no ionic, there is purely covalent, and there's just stuff between. So a bond is a bond. Now we get to metallic bonding over here. We didn't really discuss it very much. Metallic bonding is still up for debate even in some areas. It's highly studied, and essentially what it is you have a whole bunch of electrons holding metal together, and we call those electrons the electron pool. So essentially, if you took a couple different metals and you put them together, their electrons, which easily ionize, right? Electrons like to move around in metals, will move around and kind of keep everything together. It's called electron pooling, and that is the extent to which I'm going to talk about metallic bonding. Okay. Now, let's talk about ionic compounds. Which now you know is a lie. We're talking about things with mostly ionic character. So things with mostly ionic character, it will form what's called a lattice. So let's look at sodium chloride again as an example. So what a lattice is it's a three-dimensional structure. Oops. Where all the sodiums and chlorides are like attracted to each other. So sodium will be surrounded by a bunch of chloride, and chloride will be surrounded by a bunch of sodium, and it looks something like this. Imagine this in a three-dimensional structure. Cool? And so it's called a lattice. Kind of looks like a fence lattice because it's patterned in such a nice, pretty way. We call this sodium chloride, because the most reduced formula is for every one sodium, there's one chloride. But the truth of the matter is, if you pick up salt in your salt shaker or whatever, and you look at it, it's actually millions, billions, 10 to the 20, 30, and if you're holding 58 grams of it, there's a whole bunch of sodium chlorides in one little sample. And they're all lined up as nice as they can possibly be. And so when we look at how strong this lattice is, we say, hey, how much energy would it take to take this sodium and this chloride, let's say you have 1 mole of this. In other words, you have 6.022 times 10 to the 23rd. A huge amount of these lined up and in a lattice. To take 1 mole of that and break it apart fully, meaning we're actually going to take these things and turn them all into gases. It's the only time you'll see an ion that's a gas. So take these, fully break them apart, turn them into gases. How much energy would that take? And that energy is usually going to be in kilojoules per mole. And it's called the lattice energy. You'll also hear me call it the lattice strength, or ionic strength, or ionic bond strength, or ionic bond energy. These are all ways that you could say this. So how we determine whether or not something's going to be have a strong lattice, in other words, be really tightly bound, is going to depend on Coulomb's law, actually. So this is somewhat different than exactly Coulomb's law. Coulomb's law, for anybody who knows that the distance would be squared, but the general principle is going to be about the same thing. The energy, in this case we'll call this the lattice energy, is going to be proportional to the charge of one thing times the charge of the other thing over the distance. And I'm going to say this, the magnitude of the charges divided by the distance. So if you have something with a big charge, it's going to have a high lattice energy. If you have something that's really far apart, so let's do this, a big charge. In other words, these go up, then you'll have to have a high lattice energy. But a big distance between the two atoms, in other words, if you have two atoms that are really big, you're going to have a low lattice energy because the distance goes up, so electrostatic energy must go down. Let's do some examples because I think that would help more than just me talking. Okay, which has a higher lattice energy, RBI or NaBr? Okay, let me pull out my periodic table over here. So rubidium iodide here, rubidium and iodide versus sodium and bromide. So rubidium and iodide versus sodium and bromide. So now we look at this thing and we say, okay, the two things that are going to affect the lattice energy are going to be the charge and the distance between two things. Well, rubidium is Rb plus and I minus, and sodium is Na plus and Br minus. Is there any difference between the charges? Hopefully your answer is no. This is +1 and -1, +1 and -1. And so there's no difference between the charges. So the thing that we have to be looking at then is the distance between them. Well, for RBI and NaBr, we have to remember those trends we talked about at the beginning of this section, which is that the radius size goes down as you go down and to the left, or it goes up as you go down to the left. It gets bigger. So rubidium here versus sodium, rubidium's going to be bigger. Again, it gets bigger as you go down and to the left. So rubidium's going to be bigger than sodium. And so I like to just draw it like this. And then we'll do a little sodium. And let's look at the bromine and the bromide and the iodide. Iodide's going to be bigger than bromide because iodide's lower. So iodide's going to be bigger than bromide because iodide's lower. And now let's look at the distance between these two things. You're looking at the distance between the centers. We have this versus this. This has a bigger distance. It has a bigger distance because these atoms, or in this case, these ions, are bigger. And so which has the highest lattice energy? Well, this had a bigger distance. So if you increase the distance, what happens to the lattice energy? It's got to go down. Let me rewrite this because it's got a lot of arrows just to make sure. We know that the lattice energy is proportional to charge over size. Let's simplify it a little bit. I don't know how Coulomb would feel, but it's proportional to charge over size. Our charges were the same, they didn't change, but our size is bigger for rubidium iodide. If our size is bigger for rubidium iodide, this means this has the lowest lattice energy. This one's smaller, so this has to have a higher energy. If it's small, that means this number goes down, so lattice energy has to go up. Okay, so our answer to which has the highest lattice energy is sodium bromide. Let's look at the next question. Which has a higher lattice energy, KCl or CaS? So potassium chloride, potassium and chloride, or calcium and sulfide. Well, potassium and calcium are both very close to each other, so they'd be really similar in size. Sulfide and chloride are also very similar in size. They're also right next to each other. So we're not looking at size now. Now we're looking at charge. Well, remember, lattice energy is proportional to charge over size. So KCl is K plus and Cl negative. Calcium sulfide is Ca2 plus and S2 minus. So again, it's proportional to charge over size. So this one has a bigger magnitude of charge overall. Again, we're looking at the absolute magnitude. So we're looking at calcium and sulfide. So 2 and 2 would be like 4, and this is 1 and 1, which would be 2. So this one has a much higher charge. If it has a much higher charge, it also has a much higher lattice energy. And calcium sulfide has to be my answer. Again, this had a 2+ charge. Over here, we got just a 1+ charge. This had 2-. Over here, just a 1-. So the overall magnitude, if you added up the magnitude of each of these charges, this one is higher, and therefore it has a higher lattice energy. All right, so what are the properties of ionic compounds? Well, one cool thing about ionic compounds is they crack. Let's talk about why that is. Okay, so let's say you've got this lattice of sodium and chloride, and you take a hammer and you hit it. Well, what's going to happen is you're going to hit something like that, and this Na plus and Cl minus will now move down. It'll actually move down. So let me draw what that would look like. So along the crack, we had the Cl minus, Na plus, and Cl minus. Where before next to the Cl minus was an Na plus, now there's nothing. Here, next to the Na plus, as we push this part down, there's going to be an Na plus next to it. And here there's going to be a Cl minus next to it. Well, like repels like, and what happens is this guy's like, no, thank you, I'm getting away from you, and it splits off to get farther away. And that's why ionic compounds crack. Pretty cool, right? Another thing about ionic compounds is that when they dissolve or when they are completely melted, they conduct electricity. There's this one dude that does science on YouTube. I'll see if I can find his video. Essentially, he just loves to melt salt. I don't know why, but it's his favorite thing. And he just is like, okay, what happens if we melt salt and we put it in water? What happens if we melt salt and we throw it on this thing? I'll see if I can find those. But essentially what he does is he melts salt. Salt can be melted. It melts a sodium chloride. I think it's like 801 degrees C. Don't quote me on that, but it's real close to that. Sodium chloride melts. But what makes it conduct electricity? Well, let's talk about it. If you have things in a lattice, so you got the Na plus, the Cl minus, the Cl minus, and the Na plus, it's really rigid. So this is solid. This is too rigid, meaning they're all stuck together to conduct electricity. In order to conduct electricity, these ions have to be able to move. They have to be able to move. And so let's look at another example. Let's say we dissolve it. Now we've talked about this on several occasions, I believe, especially when we talk about electrolytes. But when you dissolve sodium chloride, it breaks apart in water. So we have like an Na plus over here, and a Cl minus over here, and a Cl minus here, and Na plus here, and they're just like all over the place having a good old party moving around. Here we can conduct. Well, it's not very different than if we have liquid sodium chloride, which would just be a little more compact than dissolved stuff. So if you heat it up, take a bunch of salt, you heat it up, it has a really strict melting point, so it'll actually turn into a liquid at exactly that, assuming that's right. And this doesn't look any different than this picture, so this is really goofy. But just picture the fact that this can move around. Here, let's move it around. Ready? Whoa, it's moving around. And that's what makes it a liquid, is that these can move around and get in nooks and crannies. That's the definition of a liquid. And so once these can move around and get around in nooks and crannies, then this can conduct as well. So solid ionic compounds can't conduct electricity. Dissolved and liquid ionic compounds absolutely can. All right, let's talk about covalent compounds. So bond order is something we're going to use to discuss covalent compounds. It's a fancy way of saying the number of bonds, essentially. So check this out. Let's get a carbon bonded to a carbon double bonded to a carbon, and carbon triple bonded to a carbon. The bond order for this first one would be 1. For this one would be 2. For this one would be 3, because there's 1 bond, 2 bonds, and 3 bonds, respectively. Should my daughter be allowed to have chocolate milk? Yeah, baby, but remember, I'm talking to myself, so when I talk to myself, we don't come down. Here, go ahead and grab it, and it's in the fridge. Thank you, sweetie. Okay, so the strength is determined by the bond energy. This is when I normally do a really weird demonstration in class, so it's going to be a little bit harder to talk about. No, Sawyer. It's up. Okay, pause. We're gonna pause. We'll have to... Okay, I'm back. Chocolate milk has been served. All right, the strength is determined by bond energy. So again, I said I normally do a really weird demonstration. Instead, I'm just going to try to draw it. This is really gonna be weird, but I'll do my best. Okay. So let's say you have two people, and they are not being careful with quarantine, and they're holding hands. And let's say you play Red Rover. So somebody runs through them and they can break that apart, right? This would be like a single bond. It's easy to break. What kind of energy does that mean it's going to have? Well, if it's easy to break, it's going to have low energy, low bond energy. It doesn't take a lot of energy to break it. Now, let's say they hold hands like this. And you Red Rover this, meaning you run through and you try to break their arms apart. You run through and try to break their arms apart. It's going to be a little harder, right? This is a double bond. Looks meant to represent a double bond. This is a little bit harder. So it's got a little bit higher energy. Now a triple bond, imagine us doing this in class. You guys are so lucky I didn't have to call volunteers. You do this. And then why not just pick your leg up and do that for a triple bond? Now, if you got real flexible legs, have somebody try to run through you and break you apart. Now, it's way harder. This is a triple bond. And this would be the hardest, most difficult one to break. This has the highest bond energy. Again, bond energy is how much energy it takes to break something apart. So the strength is determined by the bond energy. And what determines those things are two things. We just discussed the bond order. So I kind of went out of order there. The bond order is all this stuff. So an increase in bond order leads to an increase in strength. Remember that single is less than a double is less than a triple. And the size, the distance between two atoms. So just like with ionic compounds, if you have like two small things versus two big old things, this one is going to be stronger than this. So this one will be weaker. All right, let's go ahead and do these examples to make sure that we understand and that it makes sense. So list the following in terms of increasing bond energy. So we have SF, SBr, and SC. So it looks to me like all of these have S, so that's the thing that's going to be the constant. But what's changing is F, Br, and C. Well, what's the difference between F, Br, and C? Well, if we're looking at this, it appears to me to be size. F is going to be real small. Carbon is going to be really similar to this. If you remember, fluorine's smaller than carbon. And then here we've added a couple more shells by the time we get to bromine. So bromine's going to be the biggest. So fluorine is going to be the smallest. Let me see if I can do it this way so we can make sure we still see it. Fluorine is going to be the smallest. Bromine's going to be the biggest. And carbon's in between. So essentially we've got S. It's the same in all cases. I'm not paying attention to specific magnitudes. I just want to give you a general idea. So I'm going to draw them all the same. When sulfur is bonded to fluorine, it's bonded to a little one right there. When sulfur is bonded to bromine, bromine's huge comparatively. And when sulfur is bonded to carbon, It's actually relatively similar, a little bit smaller, and that would be carbon. So the way I like to think about this, other than looking at the ionic and just ionic strength kind of comparison and comparing the distance between the two centers, so you can compare the distance between the centers, and this one's automatically going to be smaller. Another way to think about this is how well can they hug each other? Sounds weird, but imagine that sulfur has arms. Who can it hug the best? Fluorine or bromine? It's way harder to hug bromine and get a good grip than fluorine. And so this has a better hug. So this has the better bond strength. It's stronger bond. The tighter you hug somebody, the harder it is for somebody to pull that person off of you. And the exact same concept here. So the smaller this one is, the higher the bond strength, the higher the bond energy, because those are relatively interchangeable terms. Okay, and over here, really hard for this sulfur if it's got arms to get a good grip on this bromine. So it's got a decreased bond strength and decreased bond energy. Okay, so one more time, just to kind of lay it out there. It wants us to list it, so let's go ahead and list it. They all had single bonds, so we weren't looking at bond order. Again, there's two things that affect it, bond order or the size. So we look at size. The smaller things are, the higher the bond strength is. So when looking at these, we said, hey, fluorine's up and to the right on the periodic table. It's smaller than bromine, which is down closer to, which is down. And so fluorine's going to be the smallest, therefore it's going to have the highest bond strength. Okay, let's move on to the next question. I won't draw pictures of people for you again, but hopefully you see this immediately and you're like, hey, I recognize right away that this is a single bond, and so it's going to be weaker. Something weaker is going to have lower energy, bond energy. Whereas a triple bond here, there was no triple bond, so I implemented it with an underline. I know that looks funky, but hopefully you get the gist. This is going to have increased bond energy. It's going to be a whole lot harder to pull this bond apart, this carbon from this oxygen. And so if I were doing this in order, carbon, oxygen is going to be less than carbon. Double bonded to oxygen is going to be less than carbon. Triple bonded to oxygen. So some covalent properties. So it has there are strong bonding forces within the molecule. So what I mean by that is this. Let's look at water. Water is, as we'll come to know it, is this. It's got 2 hydrogens and 1 oxygen, and this bond right here.
You know where Ashland's over is melting on some more ogres.
Sawyer, I'm talking, and I'll get it with you in a second, okay? 2 minutes. Can you give me 2 minutes? Thank you, sweetie.
It's almost like slide time, right?
No, not even close. So, water, she wants electronic time. They get 10 minutes of electronic time a day. Okay, so here we have H bonded to oxygen. Those forces hold really tightly this molecule together. So hydrogen's bound to oxygen, oxygen's bound to hydrogen, and they all love each other and they form a tight-knit group. They have strong forces holding them together. But if we take a bunch of those and put them together, and let's say we have a nice little glass of water, if you start boiling off that water, what happens? So that's my symbol for heat. If you start boiling off this water, what's going to happen is it's going to boil and water will leave like this. Does that mean any of the bonds here are broken? No, the bonds here didn't break. It just boiled, meaning it let go of any kind of attraction it had to the other molecules within it. That's very different than things that have high lattice energy. Things with high lattice energy, they're all breaking apart. They all are breaking apart. But here, when we're talking about mostly covalent compounds, they're strong within each other, but the bonds don't break just because something boils. Boiled water is still water. And this is something I see asked again and again and again on exams. So keep that in mind. When water boils, the bonds don't break when things boil. All right, they're poor electrical conductors, meaning you can't conduct electricity. If you put, first we know that pure DI water, distilled water without electrolytes, is a poor conductor of electricity. If we went and added like sugar to that, for example, sugar is a covalent compound, it wouldn't increase the conduction of electricity anymore because sugar does not dissolve as an ion. Finally, we skip the IR section. So this is unanimous between all people in our chemistry department. So we won't be going over the IR section. So we're pretty much done with what I wanted to talk about today, and I will see you all next week. Have a good one. Or not see you. I'll talk to you next week. Bye.